Yeah, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Oh, okay. Yeah, screen is visible.
Yes, sir.
Yeah, very good morning. And so the last session, we have defined the axiomatic approach for probability. Okay, and we have seen three conditions, right? Probability of an event is non-negative, and another was that countably infinite additivity, you can say, named as if you have a countable collection of mutually exclusive events, and if you take their union, their probability is going to be the summation of their each probability of the each event, and then probability of the full sample space is 1. We have also defined the definition of conditional probability, which is right probability of means like if you have a certain scenario, or you can say you have a prior knowledge that such means some random experiment had happened, and you know that some very specific things from there is also happened. It's like we have seen one example, like if you roll a dice of pair of dice, or then if you know in advance that the sum on the faces of two dice is let's say 10, okay, then in that case, what is the probability of probability that that the first dice shows 5 or first dice shows 4, okay, and so on. Okay, and then we have defined very important results in probability named as theorem of total probability and Bayes theorem. And we tried to solve some examples, and you might have found one or two extra examples in the recording as well. Okay, right. And yeah, tutorial will also focus on them. So you have now enough stuff to relate there. Okay. Now, the very interesting thing means like when you have the conditional probabilities, immediately you have means you can think of means like when we say that these two events does not depend on each other, or in other words, when you will say independence of two events occurs. Okay, so it's very natural, okay, to have this definition independence of two events, which is here, this third. Okay, let me choose this color. So this third one is the definition of independent, which is not straightforward. So means you have a probability of A given B. When B has occurred already, what is the probability that the event A has occurred? Okay, if you somehow establish that this is equals to probability of A, means it does not affect the occurrence of the event A. Okay, so if you solve out this by using the conditional probability formula, you actually land up to this. Okay, actually land up with this definition. Okay, so it is means like either way, means you can prove now probability of A intersection B if it is equals to probability of A into probability of B. Okay, then you can see that A is independent of B, or vice versa as well. So vice versa means you can if A is independent of B, you can also say B is independent of A. Or in summary, you can say A and B are independent events. Okay, so both the cases will lead to the same case. So probability of B given A is equals to probability of B if it is so. Okay, both together will lead to the special case third one. Okay, now means see then you certainly, so this is not always true, means like this should means probability of A intersection B is equals to probability of A into probability of B. Okay, so there are three possibilities in these cases. Means the relation between these two sides, left hand side and right hand side. Okay, so first case you can think of is maybe less than. The second case you can think of is greater than, and third case is equal to. Okay, so equal to answers that the events are independent. Okay, and then greater than, if it is greater than, it is positively associated. What does that mean? Okay, so if you try to relate with this conditional probability of A intersection B is greater than probability of A into probability of B. So they are positively associated. What does that mean? Means like if you see, whenever you are doing this, so if probability of B is so in this case strictly greater than, okay, means none of them is zero. Can I say that? Means probability of A is also non-zero and probability of B is also non-zero. Can I say that? Okay, if it is zero, this is obvious. Probability of A is zero or probability of B is zero. They are obvious. So you can take that means because this is always true, means may see greater than, but it may also equal to, right? Probability of A intersection B is so see if you recall that if you have two events are related, monotone property. Okay, if you recall this A intersection B is subset of A as well as subset of B. So the monotonicity of the probability function tells you that probability of A intersection B is less than equals to probability of A as well as also less than equals to probability of B. That you can prove by using Venn diagram, and you can create two mutually exclusive events and you can show that. Okay, so I say this, so probability of A intersection B is, so I can surely assume that neither probability of A is non-zero, and I mean this is true, probability of B is also non-zero. In that case, I can, without loss of zerity, I can assume this, both are non-zero probability. If they are zero, its probability of intersection B is also zero, that's strictly greater than will not happen there. Okay, so I can assume this. Now, what is this? So probability of A intersection B is greater than probability of A into probability of B. What it tells you? That probability of A intersection B divided by probability of A is greater than probability of B. So this is why this non-zero thing is essential here. Okay, non-zero means is strictly greater than zero, right? And you can divide both sides by positive number, then inequality will not be altered. This is what it means. So what is this? The left side is probability of B given A is greater than probability of B. What does this tell you? So occurrence of the event A enhance the probability of the occurrence of the event B. So this is why it is known as the positively associated. Okay, so in the given that that A has occurred, in that case probability of B is more than the actual probability, means this is enhancing the chances. Okay, so this is why it has the attached name is the positively associated. Okay, similarly you can explain for the negatively associated case. When you have the less than, the chance of the probability of occurring B is going down, means like means like decreased. Okay, so it has negatively associated, they are negatively associated, we say. Okay, right. Now let's let's have one example here. So two fair dice are thrown. Okay, so your two dice are thrown. So EI is the event that sum of the dice is 7. E2 is the event the first die is equals 4, and E2 is the event the second die equals 3. Okay, so you can certainly write down all these event these spaces. Okay, these things you can easily write down. Okay, right? You can easily write down this. Sum of the dice is 7. The E2 is the first die equals 4. That also you can write it. Okay, that also you can write it. That you have the first die equals 4 means you have 4, 1, 4, 2, and so on, 4, 6. That also you can easily write. Similarly, you can have this one second die equals 3, like 1, 3. Yeah, 1, 3, 2, 3, 3, 3, 4, 3, and so on, 6, 3. Yeah. Now, what is the purpose of having this example is as follows. So you can find out what is the probability of E1. Is getting the sum of the dice is 7. So how many of the pair are 1, 2, 3, 4, 5, 6, and occurring of each pair is equally likely. That's 1 by 36. So you have 6 by 36. So that's going to be 1 by 6. Okay, so probability of E2 also 1 by 6, and probability of E3 is also 1 by 6. That also can be proven. Okay, right. Now you can verify the following. Okay, probability of EI and EJ happen together. What is the probability of EI and EJ? So that you have to. So you have E1, E2, E1, E3. It is so. So you need to look at the case. What is the probability of E1 and E2? Okay. So now what is the probability of E1 and E2 means both happen together. Sum of the dice is 7 and the first die equals 4. So you have 4, 3, right? So you have, this is going to be E1 and E2 is first die equals 4, right? So E1 and E2 is equals to 4, 3. Both happen together. Is going to be, this is occurring of this, and that's going to be 1 by 36. And I can certainly write 1 by 6 into 1 by 6. That's equals to probability of E1 into probability of E2. Similarly for others as well. Okay, so you can similarly you can also show that probability of E1 and E3. So second die equals 3. So you have again the same event. Okay, again you will have this. Now, what about E2 and E3? So first die equals 3 and second die equals 3. First die equals 4 and second die equals 4, 3. Again, you can establish that. So they are pairwise independent. Okay, so they are pairwise independent. Okay, so you take any two, you can prove that. Now, what about all are independent? Can I say all are independent? So E1 intersection E2 intersection E3. Can I say that's equals to probability of E1 into probability of E2 into probability of E3? No.
No, sir.
So because probability of E1 is, so all these things are you are having. So E1 intersection E2 intersection E3 is nothing but the 1 by 36. That 4, 3 only. Okay, so if you, I just want to state this here. So if you look at this E1 and E2 and E3, that equals to the pair again 4, 3. 7. First die shows 4, second die shows 3. So all those together. So probability of E1 intersection E2 intersection E3 is equals to 1 by 36. But that is not equals to probability of E1 into probability of E2 probability of E3. So I can say also that E1 is not independent of E2 and E3, and E1 and E2 is not independent of E3. And I think, right? So what is the purpose of showing this example is they are though mutually exclusive, means pairwise independent. Okay, may not be all of them are together independent. Okay, so this is why this, see, to generalize this to any case, this is why this definition here is taken as follows. So probability of A intersection B, so 2 events. So you can generalize to 3 events. Probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. If we say A, B, C are independent, and so on. Okay, so here we have an example of pairwise independence, but not independent. All are independent. Okay, right. Now, so with this, all the definitions, we will move to the case 4 now, which may be also, I think, I don't know whether you are aware about the random variables so far or not. Maybe it has been encountered with your some of the course. I don't know. Okay, but I will start from the basic only. Okay, so this random variable. So both are, I think, known to you. Random is randomness will be there, and variable means it's variable. It will change. Okay, it's a function. Okay, so why do you need that is also a question sometime. Okay, so here I'm just starting with an example. Okay, of a random experiment of rolling a pair of dice. Okay, you have written the full sample space. Okay, you have written the full sample space. Okay, which is here. Now we are not interested in this sample space. Rather, we are interested in the sum of. Okay, sum of ing. Okay, so or you can also have this maybe difference. Okay, that also possible. Okay, I can also I can say this is S1 and I have this is S2. I may have the difference, so I minus j. So I think it is very easy to get, so minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. Right? This is the maximum. Wait a minute. Yeah. Right? Minimum is minus 5 and maximum is 5, and all of the integer between them. So I may be interested in the difference. I may be interested in the product. Okay, I may be interested in the product as well. So S3. So you can write all the possible products here. So there will be 36 number of them. So I don't want to write. So you have, this is I into j. Okay, such that I is equals to 1 to 6 and j is also equals to 1 to 6. I may write in this form. Okay, so now you want to ask yourself, what is the probability that their difference is minus 2? What is the probability that their difference is their sum is 4? What is the probability that their product is 36? Okay, and so on. Okay, so now this so let's consider this case. Okay, S1 is sum of the two dice. Okay, so we are interested in assigning the probabilities to them. Okay, so now what is here is means we are interested in a function. Okay, we are going to define a function now, x. Okay, on S2R, or not S. We are defining a function x on the sample space to R. So omega is the full sample space, set of all possible outcomes from a random experiment. And here we have an example. So we are working with that particular example. So example, so you have any event. So it is enough to define for individual event. Okay, and that's going to be the sum of them. Set of all possible pairs. Okay, so the event means I plus j. You note it down, I and j, and take the sum. So what is here is x can take, so x of omega. So that's how you define the range space. So x of omega is equals to s, that s where s1. Okay, so that is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the range is this set. Okay, so range is finite here, right? Finite set. Okay, right. Now, also what we are interested in now, assigning the probabilities. Okay, so now here onwards, we are maybe going to use so-called abuse notation. In the mathematics, it is known as abuse notation. Okay, so I want to assign the probability of x equals to w, or let's not x equals to s. So let me make you understand what is the meaning of x equals to s. It is like x equals to s is is defined as x equals to s is the abuse notation for this set. All w belongs to s such that x of w is equals to s. So in short, it is defined by this. Okay, so this is why we are saying that this is a abuse notation, because here w is omitted, silent, you can say. Okay, so I think now you may also get what do we mean by x less than equals to s. Okay, this also can be easily identified. That's going to be w in s such that x of w is less than equals to s. That also. Okay, this notation you are comfortable with now. Okay. Now, so it is now, it is now easy to identify the probabilities of getting a sum is 2, 3, 4, 5, 6, right? You can assign the probabilities. How? So let's, so now for probability of, let's say, x equals to, I'm just going to randomly, I'm choosing this, let's say 4. Okay, this is an event. Okay, this is set of events, x equals to 4 this is a set of events such that W in S, such that, not W in S, I think W in omega, such that x of W is equals to 4, right? Oh, this is omega, okay? Now, this is, what is this? This is set of events. So this is equals to x of W is 4. So you have all the possible pair 1, 3, 2, 2, and 3, 1. These are the possible 3 pairs. So I can certainly identify this with a probability is going to be 1. These all are equally likely. So probability of getting 1, 3 plus probability of getting 2, 2 plus probability of getting 3, 1. So 1 by 36, 1 by 36, 1 by 36, 3 by 36. So I have assigned this for x equals to 4. Similarly, I can also assign, let's take one probability of, I'm just going to give one example. So x equals to 7. Let's take this. So it's going to be the set of events omega such that x of W is 7. So you can find out all the possible pair 1, 6, 2, 5, 3, 4, right? 4, 3, 5, 2, 6, 1. So 1, 2, 3, 4, 5, 6 all are equally likely. If you take individual, they are mutually exclusive. You can apply the countable additivity property here. And so this is equals to 6 by 36. You can assign the probability this, and so on. Okay, right. Now, so you have, let me come back here. Let's say here. So I have all this. Okay, so I have defined here all the possible assigned. I have assigned the probabilities for each case for the range space s equals to 2 to 10. Let me have made it S1. It's fine. Now you can also look at it carefully. One thing, so that we will take off. We will also consider it later on when we define the discrete random variable, these properties. But you can certainly identify that each of them is non-negative, is greater than equals to 0. That's the very first thing. And secondly, if you sum up all, so 1 by 36 plus 2 by 36 plus 3 by 36 plus 4 by 36 plus and so on, these you sum up, this is also going to be equals to 1. Okay, so other than these values, x equals to, so you may ask the question that you have, this is defined x from omega to r, so any real value. So x can take any real value, of course, but for other values, so means except from the S1 case, the associated probabilities you can define as 0. Okay, that probability you should define as 0. Okay, right. So this is somewhere I can mention also, this is called, this is somehow I can also name as that probability mass function, on this example of a discrete random variable. I'm just giving you a hint. Maybe we will recall it. Okay, later case. Okay, now let's come back and let's define the definition of a random variable. Note that this whatever we have considered so far, that random variable for the corresponding random experiment may not be unique. Okay, so for example, you can consider the difference of the difference on the 2 dice, right? You can also consider this S2 difference on the 2 dice. You can also go for this. You can also go for this. So non-uniqueness is there. So randomness is attached with it. Okay. Okay. Now let's let's call it formally now. So let's say, so a random experiment. So let a random experiment be formed and omega be associated sample space. Then a random variable, say x, is a real valued function defined on omega. So that is this, x from omega to r, which associates a numerical value to each event. It's very clear. Okay, right. So let's move forward now. So you have we have done all these things. I don't want to repeat it. And I have also mentioned this. What is this abuse notation? Okay, x equals to s means this is. Okay, right. So this is, it's not abuse notation. Okay. Now, also, I have told you that you can also verify that summation I equals to 2 to 12, they are mutually exclusive. And if you sum up all the probability, that will lead to 1. Okay, that we have shown. Okay, right. Okay. Now, let's take another example now. Okay, so suppose a person purchases 2 electronic components. Okay, 2 electronic components, each of which may be either defective or acceptable. Okay, let's define D as the defective and A as the acceptable component. And it is also given to you that both are defective will be with the probability 0.09. Okay, one of the defective, so first is defective, second is acceptable, or first is acceptable, second is defective. Okay, both are treated equally likely case, and you have this is probability 0.21 each. Okay, and the case both are acceptable is with the probability 0.49. Okay, now you can define the random variable here. Okay, as follows. So let's denote this x as a number of acceptable components obtained during the purchase. Okay, number of acceptable components obtained during the purchase. So x can take, so either none acceptable, one acceptable, or at most 2. So that can be only possible x in the range space. Okay, now x equals to 0. If you follow that abuse notation, what that mean is none of the component is acceptable. And if you go back and check, none of the component is acceptable, assigned with the probability is 0.09. So that's what is assigned. Now the second case, x equals to 1, means one of the component is acceptable. So either first or second, doesn't matter. So 0.21 plus 0.2. So that's going to be 0.4. And x equals to 2 leads to the case both are acceptable with the probability 0.49. Also, so now you can also, one more thing also you can note it here, that each probability is greater than equals to 0, greater than equals to 0, greater than equals to 0, and their sum is equals to 1. Okay, so again, we are going to define them as a name as probability mass function later on. Okay, so this is one definition of. So you can, instead of number of acceptable components, you can define x as a number of defective components obtained during the purchase. Or you can also there is a one very famous random variable known as indicator random variable. Okay, so let's define it here. So let I denotes the event that this event that A occurred. Okay, so A is the event that at least one acceptable component is obtained. That's the event occurs. So that if you name it as A, so this is IA here. So this is called indicator, means like switch off, switch on. Okay, so it will take only binary number. So either 0 or 1. See, these are numbers. So this is a choice. Instead of 0, 1, you can also take -1 or 1. Doesn't matter. But in the practical purpose, that will be chosen as 0 and 1 as for comfort. Okay, so you can, instead of this, you can also use any other values. Okay, -1, 1. Okay, or 2, 1, any real value. Okay, now, so indicator random variables, it will, as a practical point of view, we will take as 0 or 1 either. So either event occurred or does not occur. Okay, so if event occur, it will take the value is 1, and if event does not occur, it takes the value 0 right now. Okay, so if A occurred, so 0 means if A does not occur. Okay, means the case is x equals to 0. Okay, and if event occurred, the case means either the number of acceptable components is 1 or x equals to 2. Okay, and any one of them. Okay, so event A occurred, event A does not. Okay, and now this is, you have IA is not as the indicator random variable, and you can assign the probabilities to each value of. So IA equals to 0 means does not occur with probability, means no component is acceptable, means defective component, and it will come with the probability 0.09. And you have another random variable. You have another value of indicator random variable, that is 1. Is the case that event A occurred with the so either x equals to 1 or x equals to 2. Both are mutually exclusive events. So probability of x equals to 1 plus probability of x equals to 2. So that's going to be 0.42 plus 0.49, right? So this one, this one, this one, all this sum up. Okay, so that's going to be total is you are going to have is 91, right? 0.91. So that's going to be this. And note that again, if you sum up these two, it's going to be the 1, a non-negative case. So again, it will identify the probability mass function. Okay, right. Okay, now you have one example here for the case when you have the range space is you can say is countably infinite. So far you have dealt with the countably finite case. In the similar fashion, you can also deal with the countably infinite case, and you can assign a random variable there. Okay, so it's a very famous example. Okay, which will occur many times, so again and again, repeatedly. Okay, so it's the experiment again. Toss a coin repeatedly until it occurs. Okay, so this is a sample space that is easy to get. Okay, and we assume that the toss is so coin is fair enough. Okay, and getting the probability of head is 1/2, probability of getting tail is 1/2. So we have dealt with this case many times. So this x, there are again two I can identify right now two ways: number of tails in W or number of heads in W. Okay, so you will count the number of head, and that will be the value assigned to the x. Okay, so number of if you assign number of tails in W, so first event you have this is right, so you can name it them as a W1, W2, W3, and so on. Okay, and I think number of heads in W is always 1, so there is no point of defining that, right? Okay, so in that case suppose if you define that number of heads in W, then what will happen? All are 1, right? So probability of getting head, so number of head in W is 1. In each event, number of head is 1. Okay, so either x can take only one value, fixed value, constant. This is a constant random variable, right? So we have got an interesting thing here. So if I assign x of w is equals to number of heads in w. So that's equals to 1 for all w. It's a constant random. Okay. And what is the probability mass function? So constant random variable. The probability of x equals to 1 is 1. Surely. Every event is having, this is going to be probability of x equals to 1. You can assign this one only. Right? Okay? Right. So instead of that, so to make it more interesting, we have taken the case number of, this is a constant random variable. So number of tails in W. So number of tails could be 0, 1, 2, 3, and n. So set of natural number union with 0, again a countable set. So countably infinite is not a problem. Now x equals to 0 means you can relate them now. 1 by 2 means number of tails in W is 0, means only one, right, head. So it's equating with probability is 1 by 2. Probability of x equals to 1 is th. Okay, so first is means like they are simultaneous task again. So probability of getting tail into probability of getting head is going to be 1 by 2 into 1 by 2. So 1 by 2 square. So and so on. You can verify that probability of x equals to I is equals to 1 by 2 to the power I plus 1. So you can establish all the facts now that is these all are greater than 0, greater than equals to 0, greater than equals to 0, greater than equals to 0. Also, you can also establish the fact that summation of this you can also establish that summation I equals to 0 to infinity 1 by 2 to the power I plus 1 is going to be 1. That also you can. Okay, so again, this will identify as a probability mass function. Okay, right. Okay, so now we can define the definition of a discrete random variable. So a random variable whose range is either a finite set or countably infinite set is called a discrete random variable, as simple as. Okay, so which assumes only the discrete values, you can say, not in the continuum, or not like continuum case, means like any value between, let's say, 1 to 2, 1.5 also it can assume, or 1.6 also you can, or 1.499999 also it can be assumed. No, it's a discrete random variable. Okay, so can you give an example where x cannot be discrete? Yeah, can you give an example?
Sir, the event of choosing a point from 0 to 1 on the number line.
Okay, can you give a life? Can you give a real life example?
Sir, the time between 12 o'clock and 1 o'clock.
Yeah, great. Or indeed, if I want to measure the lifetime of a car or lifetime of a person, okay, then your measure units are
velocity,
anything. Huh?
velocity of any moving object.
Yeah, velocity of any moving object, that also random, will change. Yeah, so fantastic. So you're good enough.
Sir, the range of ball when it is struck by the bat.
TPI of students.
Pardon? Students. I didn't get you. Okay, let's move that. So, okay, so you have given very good examples. already, the pair that that random variable can take a continuum of possible values. Okay, weight, gain, number of years. Okay, or can you give an life? Can I give a real life example where you have countably infinite? Okay, let me help you here. So, for example, you can take the number of phone calls in a day. Okay, number of phone calls in a day that can be countably infinite. Or in a day or in a year, you can say, right? In a day, instead of in a day. If you make it a large set now, in a year, it will be countably infinite. Okay, right. Now, another very important definition is of cumulative distribution function. Okay, and this is how the definition is. Okay, so it's very clear from here that fx, so x is denoting the dependence of this. Okay, cumulative distribution function is related with this random variable x, that only showing this f suffix with x. Okay, so for any real values x, so x is any value from the set of real number, and the right hand side is a probability. Okay, so total probability x less than equals to x. Okay, so so probability function, you know what is the range is at least 0 or at most 1. So the range is lies between 0 to 1. Okay, right. So now we try to relate with the previous examples. Okay, so the very first example is we have considered is the rolling of 2 dice. Okay, rolling of 2 dice. So we are interested in finding the CDF of this. We have already assigned the probabilities for each sub value. Okay, now if you consider the value x is any value, x is any less than 2. So the sum is less than 2. Probability of x less than equals to x. How will you read it? If you if I recall, x less than equals to x is probability of set of all w in omega such that x of w is less than equals to x. Okay, now if you read this as this, then set of all events for which x of w is strictly less than 2, means sum is less than 2, is impossible event. So you have the probability is 0. Now if you go to the next level, 2 less than equals to x less than 3. So how will you look at this here is, so again 2 less than equals to x less than 3. So it is all possible events with sum is greater than equals to 2 but less than 3. So it is essentially is equals to probability of you have 2 less than equals to x less than 3. So this is nothing but probability of x equals to 2. Okay, so that's probability of x equals to 2 is 1 by 36. Now, when you move to this event now, 3 less than equals to x less than 4. So any x which takes value more than 3 and less than 4. This is how it will you will read. So if you look at carefully the definition, it is 3 less than equals to x of w less than 4. Right? Or x of w belongs to this, right? 3 to 4. So it can take, so the value x equals to 2 and it can take the value x equals to 3. These two possibilities here. But both are mutually exclusive cases. So this is equals to probability of x equals to 2 plus probability of x equals to 3, and then you can fix their probabilities here. So that is going to be 3 by 36. Right? So this side is real value. Okay, x of w. Okay, so now similarly here you will have probability of x equals to 2, x equals to 3, and x equals to 4, and so on. Okay, so that's going to be 6 by 36, and so on. So what you're observing is here, can you observe the nature of this function, distribution function here? Yes, can someone tell? What is the nature of this one? Yeah, increasing function, yes. And also in more precisely, it is also a step function. Okay, if you are going to plot it, it's going to be increased. Okay, right. So you have this here. So I have written down all the possible things here, so that you can later you can match with your results. Okay, so fx is a step function, it's an increasing function. Okay, right. Okay, now let's try to look at this exercise. Probability of a less than x less than equals to b. I am interested in finding this. I don't know. See, so far this cumulative distribution function does not tell you whether it relates with discrete or continuous. So both the cases, discrete or continuous. Okay, continuous so far we have not defined yet. Okay, but this definition will exist for both the cases. Okay, right. So now if you look at this carefully, a less than x less than equals to b, and now if you write down this is the event. This is a set of all events such that this happens. Now, if you look at this graph, okay, this graph here, I can write this this event. So a less than x less than equals to b lies here, right? Suppose a is here, this real value, and b is here. Okay, so this a less than x less than equals to b is here. Now, if you look at carefully, this is nothing but x less than equals to b, this complete one. Okay, till here, and it is from till here, it is x less than equals to a. So I can write this x less than equals to b as a union of these two. So x less than equals to a plus x a less than x less than equals to b. So this is set. So this will plus means union. Okay. So but both are mutually exclusive. Both are mutually exclusive. So what it tells you is probability of x less than equals to b is equals to probability of a less than x less than equals to b plus probability of x less than equals to a. In the discrete case, point does matter, but in the continuous case, you will see the point does not matter. Now, if you look at the definition of fx, the cumulative distribution function, the left side is fx at b is equals to probability of a less than x less than equals to b plus fx at a. So this will establish the formula. Okay, right? So you can, so similarly, you can go for now then a less than equal to x less than b. That also, if you try to do this, if I want to get this exercise, so probability of a less than equals to x less than b. Okay, so what it is, this is equals to, I'm going to write probability of what it is. If you look at the graph carefully, it is going to be wait a minute. So a less than equals to x less than b. So I know x less than a is equals to, or x less than b, okay, is equals to x less than a union a less than equals to x less than b. So this tells me that probability of x less than b is equals to probability of x less than a plus probability of a less than equals to x less than b. Okay, so probability of a less than equals to x less than b is equals to probability of x less than b minus probability of x less than. So if you look at the definition, so I may write it as b minus, right, and a minus. I'm just trying to write fx at b minus minus fx at a minus, a negative. If you recall, this is limit x tends to a minus, x b tends to b x tends to b minus. That also can be represented. Okay, so things will change when you don't have the continuous case. Okay, so continuous case, it will be still come out at fx b minus fx a, because this point does not matter in the continuous case. You will see why. Okay, little later. Okay, right. Now this is I have done this. Okay, so this example I will skip here because this did not. This is the case for the continuous random variable, though it is solved in the recorded lecture as well, so you can watch there. Okay, but it's very easy to get it. Okay, so I will come back to here. Types of random variable, let's define now clearly. Discrete random variable. A random variable x is called discrete if its range is either finite or countably infinite. Okay, so it is very clear. Now, in this case, we define the probability mass function. Okay, we define the probability mass function, which we denote it as p dot m dot f of x by following. Because x assumes the discrete values, okay, x assumes the discrete values, so it can take equals to a. Okay, a is from where a is taking. So you have taking a is from the set of range space. Okay, so you have this is x belongs to not x here, a belongs to this x of omega. Okay, right, and this PMF has the following properties: this non-negativity, and this is called normality condition. Okay, normality. This sum up is if sum is equals to total sum is equals to 1. Okay, right. So if you have, in other words, if you are able to identify a function, okay, which is defined on defined on the real number, okay, and its sum, total sum is equals to 1, that is going to be a probability mass function for certain discrete random variable x. Okay, and if x is a discrete random variable, you will be certainly get this. Okay, right. Now, so we have done this example. So write the PMF of example 1 and example 2. So example 1 was rolling a dice. Okay, so rolling a dice with sum, with your noting sum is S1 is 2, 3, 4, 2, 12, and we have done this thing. Okay, px of 2, px of 3, px of 4, and so on, px of 12, and you can prove that their sum is equals to 1, and we have done this. Okay, so for just let me say here what is px of I is equals to probability of x equals to I, where I belongs to this S. Okay, when if you take x equals to 3, it is 2 by 30. I equal to 3, 2 by 36. If I equals to 12, it's 1 by 36. And if these are all are non-negative, and sum is equals to 1. Okay, right. Now Similarly, for the next case, there are two random variables we have defined. One is the number of acceptable components. Okay, and that IA is the indicator random variable when the event A has occurred. Okay, so we have here, now this is by definition, probability of X equals to 0 is none of them is acceptable. This is probability of X equals to 1 means one of them is acceptable. Probability of X equals to 2 is both of them are acceptable. Okay, other than that is 0. Similarly here, event A does not occur, here event A occurred with the probability. So both satisfies the probability mass function definition. Okay, right. Now, this is another example, which is again, I think this can be solved straightforward. Okay, which is saying that you have been given with the definition of a random variable which takes the values 1, 2, or 3. Okay, assume that we know the following. The probability Px of 1 equals to 1 by 2 and Px2 is 1 by 3. Okay, then what is the value of Px of 3? It is very simple. So Px of 3, and here it is also given to you that it is not given to you. So this is a very straightforward result that Px of X is 0 if X does not belongs to 1, 2, 3. Why? Because X can take only these three values, 1, 2, or 3. Other than that, it cannot take, well, they are impossible events, so they can be assigned as 0 values. Now you can use the normality condition to find the Px of 3. Okay, so what is the normality condition is, okay, so what is the normality condition is this. Summation Px of X belongs to R equals to 1. Now this is equals to Px of 1 plus Px of 2 plus Px of 3 plus some other X values from the real number, but they are value with 0. So there are no need to write here. Equals to 1. So Px of 1 is non, Px of 2 is non. So you can find Px of 3 is equals to 1 minus sum of them. So that's going to be easy to get, 1 by 6. Okay, right. Now let's this example, this exercise already done. Discuss the nature of CDF for a discrete random variable X. Fx is a step function. Okay, let us define the definition of continuous random variable. Okay, so we say that a random variable X is continuous if there exists a non-negative function f of X, which is defined for all X in this real number, having the property that this one. Now, as I hope I have done this Riemann integrable criteria somewhere, okay, in your earlier course, calculus course maybe. So where what you have seen is you have first you have defined the partition of the interval AB and suddenly generalized to the integral. Okay, that finite sum, and then you are let n tends to infinity. That's going to be the integral case. So similar here. So here PMF and this density function, they are somehow, as you can say, roughly they are related like a limiting cases. Okay, when X can take, assume any values in between them, so summation will transfer to the integration. Okay, and now this B is any subset of real number. Okay, means X can take any value, so it could be A to B, closed interval AB or semi-closed, open, you whatever the case. Okay, so that's going to be integration A to B f of X t. So you can assume that this is the area under the curve, provided the full area is, you can say, see, you have to make it as a probability function. So what is the constraint here is the total probability should not cross 1, right? So you are going to apply the normality condition here. Okay, so that's going to be come into the picture. Okay, so you have this X, so continuum case is integration of f of X dx. Now note that, see, you cannot, you see, this is Riemann integrable criteria is only defined on the bounded interval. Okay, that's A to B. But here it's a unbounded interval, means it's an improper integral. It's going to be an improper integral. So that has to be handled specially. Okay, like improper integral of first kind, second kind, one of the limit is infinity or minus infinity, or in between some of the point is there where the function is not defined. Okay, these are the special type of improper integrals. Okay, so now to preserve the integrability of the function, this function is integrable, you have assigned the they have assigned the condition that the function is continuous. Okay, that's at least required. Okay, that you should keep in mind. Other conditions are non-negativity and normality condition with attached with this, and we will call this as F as CDF. Oh, sorry, PDF, probability density function. Okay, and also we denote this with suffix x as well to show that, or to have in mind that this F is the density function, probability density function for the given random variable x. This is the only purpose to mix here suffix with x. Okay, so this function F is called the probability density function of x. Properties are following. So if you are having any such function which satisfies this property, okay, then it is going to be a probability density function of certain continuous random variable x. Okay, right. Now, so these things you can very easy to relate. Probability of a less than x less than equals to b, or a less than equals to x less than equals to b, means x belongs to this closed interval ab, and this is what is integration a to b f of x dx. This is point probability is 0 if x is continuous random variable. That also can be verified because integration a to a f of x dx is 0 by using Riemann integral there. Fix. Third thing is what is interesting is here cumulative distribution function fx. For the case of continuous random variable, it is going to be differentiable. Okay, and its derivative is going to be the probability density function at that point. Derivative at the point is going to be probability density function at that point. So that is a beautiful relation which can be helped in many cases. Okay, so you may be following this fx of a is equals to probability of x less than equals to a, and which is nothing but x belongs to minus infinity to close a, that's your b, and integration over b this minus infinity to a f of x dx. How will you handle it? Limit case. Okay, right? So I think I have done this. Yes, limit b tends to minus infinity here, integration b to a f of x dx. Okay, so right. So now the last problem here is as follows. So that you can, again, this is the case when you have probability density function. Similar problem we have solved in the probability mass function by applying the normality conditions. You can relate here. Okay, so let x be a continuous random variable with the following probability density function. Okay, where x can take any values between 0 to 2, and these we can treat them as the associated probabilities. Okay, that we can treat them as the associated probabilities over this interval or okay. So this is going to be 0 otherwise. If x lies between 0 to 2, this has this, and 0 otherwise. Find the value of c. So first you have to find the value of c. How will you find out? By using this normality condition. Integration minus infinity to infinity f of x dx. So because since it is a PDF, you are allowed to use this. Okay, so is equals to 1. So you can have, so minus infinity to 0 and 0 to 2 and 2 to infinity. You can subdivide this integral. But only non-zero between 0 to 2. So this is why this second integration 0 to 2 f of x dx equals to 1. Now you can substitute here between 0 to 2, this value is here, and you can integrate this and substitute upper limit minus lower limit and solve it. Okay, so if you do this, so If you do so, you will find the value is C is 3 by 8. Now, once you have C value now, so now you have the full definition of probability density function. So you can easily identify what is the probability of x greater than 1. So if you rewrite this as probability of x belongs to 1 to infinity, this is going to be integration 1 to infinity f of x dx. Okay, so you have C value. So you know fx is 0 when x is more than 2. So it is 1 to 2 f of x dx, and f of x is known here with C value is 3 by 8. So you have to carefully substitute now. So x belongs to 1 to infinity fx of x dx, and 3 by so C is 3 by 8 times 4x minus 2x square 1 to 2, and if you immediately apply this, this is going to be 1 by 2. Okay, right? So this is one example for probability density function. So if you have any question, you can ask.
Sir,
Yeah.
sir, what is negatively associated and positively associated?
Negatively, that independent event I have told you there means we have this. Okay, so you have you had the you have we say A is independent of B if it is equals to probability of A, right? So means A, the occurrence of the event B does not affect the occurrence of the event A. Then we say that A is an independent event of B. So that will lead to this definition: probability of A intersection B is equals to probability of A into probability of B. Now, what can you say when you have probability of A when occurrence of B is greater than probability of A? What can you say about it? If occurrence of the event B, okay, enhance the occurrence of enhance the chances of the occurrence of the event A, means they are positively associated, means it is affecting positively. Okay, now instead of this, if you have less than here, what you can say that occurrence of the event B affect the occurrence of the event A negatively, means it makes less chances that the probability that A event occurred. Is that clear? So this is what is going to be give you the negatively associated meaning, and this is going to be give positive. Okay.
Okay.
Yeah. Okay, fine. Thank you.
Hello, sir.
Yeah.
Sir, I was having a small doubt. Sir, in one of the past examples we did for the independence of events where E1 was sum of the dice is 7, E2 was the first dice equals 4, and E3 was the second dice equals 3. Means, sir, there you said that means there E1, E2, and E3 were pairwise independent.
Yeah.
But all three were not independent. So
Yes.
there you said that, sir, there you said that E1, E2, E3 are mutually exclusive. But how are they mutually exclusive?
Mutually exclusive means pairwise. They are means like mutually exclusive events means what? EI and EJ cannot happen together.
Yes, sir. But E1 and E2 can occur together, sir, right?
Yeah.
So how is E1 and E2 mutually exclusive?
So see, mutually exclusive is see this